We will now look at some operations on distributions. So before we get started, we would like to introduce some very useful notation. So let of course omega be contained in Rn, open set. So this, whether I say it or not, again, this running hypothesis. Okay, so let a multi-index of order n is an n-tuple of non-negative integers. So alpha is a multi-index, so this will be alpha 1 to alpha n, alpha I greater or equal to 0, alpha I in Z for all 1 less than or equal to I less than or equal to n. Such a thing is called a multi-index. So having a multi-index, we define the following notations. So mod alpha is nothing but alpha 1 plus alpha n. Alpha factorial is alpha 1 factorial multiplied by alpha n factorial. And if x belongs to omega, x equals x1 xn, then x power alpha will be given by x1 to the alpha 1 xn to the alpha n. So this is a monomial here. Finally, we define d alpha is equal to d, the partial derivative, d mod alpha dx1 to the alpha 1 dxn to the alpha n. So for example, if you take n equals 2 and you take alpha equals say 2 1, so this is a multi-index of order 2, then d alpha will be equal to d3 by dx1 square dx2. Suppose n equals 3 and alpha equals 1 0 2 for instance, then d alpha will be d3 by dx1 dx3 square. There is no dx2 because the second index is 0 here. So this is how we have very compact notation for the introducing derivatives. So for instance, in this notation, if we want to if we have phi n in d omega, phi n goes to 0, that means support of phi n is contained in a fixed compact set K, and then phi n and d alpha phi n, all these sequences converge uniformly to 0 on K for every multi-index alpha of order n. Okay, so this is the way we use this notation here. So now we want to introduce derivatives of distributions. Okay, so let us start with the case n equals 1, and let us take f belong to C1 of R. So it's a continuously differentiable function. Therefore, f and f dash are both continuous, and therefore they are automatically locally integrable and hence define distributions. So now let us take t of f dash phi. So this is equal to integral f dash phi dx over R. Okay, and now you integrate by parts, so this will become minus integral over R f phi dash dx. Then there should be some boundary terms, which is evaluation at plus minus infinity of this integrand f phi, but phi is of compact support, so it vanishes at infinity, and therefore there will be no boundary terms, and therefore this is the thing. So if you look at this expression here, this does not have any reference to the derivative of f, all the onus of differentiation falls on phi, which is a C infinity function with compact support, and therefore it can be differentiated any number of times. So we use this fact. So this is nothing but minus Tf of phi dash. So we copy this in general. So if T belongs to D prime is any distribution, we define T dash as a distribution. We will see why this is a distribution in a moment, and such that by T dash acting on any phi is equal to minus T acting on phi dash. Okay, so why is this a distribution? Because, well, it's linear, it's well defined, because phi dash is also a C infinity function with compact support, and if phi n goes to 0 in d omega, then all the derived sequences also go to 0 in d omega, and therefore T of phi n dash will go to 0. So if phi n goes to 0 in d omega, automatically this implies that phi n dash also goes to 0 in d omega, because all the supports of phi n dash are all in the supports of phi n, and therefore they are all in a fixed compact set K, and all derived sequences go to 0 uniformly. So phi n dash, its derivatives are phi n double dash, phi n triple dash, etc. They will also go to 0. So this implies that T of T dash of phi n goes to 0. Okay, so the T dash is indeed a distribution. Now we like to iterate this. So let us try to define T double dash as a distribution. So T double dash of phi is nothing but T dash dash of phi. So this is equal to minus T dash of phi dash by the definition which we just gave. So minus T dash of phi dash. So now I am going to again use the definition of T dash, so that will become, and the minus will get picked up, so that will be T of phi double dash. So, and again you can check that this is a distribution for the same reason as we said earlier. So in general, if you want to define the nth derivative of T, you can now see the pattern. So this will be minus 1 power n of T of phi n, where the bracket n denotes the derivative. So the nth derivative of phi. So this is why you see having C infinity functions with compact support is very convenient. Namely, we can define all derivatives of T by simply throwing the responsibility of differentiation onto the functions phi, which can take it because they are all C infinity functions with compact support. So this is how we will define the derivatives of a distribution, and therefore let us give a formal definition. So omega in Rn open set, T in D prime omega, and alpha a multi-index of order n. Then you have the d alpha T is defined by of phi is equal to, so we define this as minus 1 to the mod alpha T of d alpha phi. For all phi in d omega. So this is how we define the differentiation of and all these defined distributions, and therefore we have that every distribution is infinitely differentiable. For any multi-index alpha, all their derivatives exist, and therefore you have. So now let us look at some examples. So first let us consider delta Dirac distribution on R. So what is delta dash acting on phi? This is minus delta acting on phi dash, and that is equal to minus phi dash 0. And if you remember, this is nothing but delta 1 of phi up to a sign, minus delta 1 of phi as I defined it. So the notation was not accidental, it was deliberate, namely up to a sign. So up to a sign, delta dash is the doublet distribution. Okay, so now let us look at another example again on R. So we define the Heaviside function. So h of x is equal to 1 if x is greater than or equal to 0 and 0 if x is less than 0. It does not matter where I put the equality, this is a function which is, it does not matter. For us it is a locally integrable function. As long as you change the value on a set of measures 0, it does not matter. So Heaviside function is the function like this. So now let us compute th dash. So this is equal to minus th acting on phi dash, which is equal to minus integral over r of h into phi dash, and h is 0 for x less than 0. So this is minus integral 0 to infinity phi dash dx, and if you evaluate the difference at the end points, and at infinity it vanishes because phi is a C infinity function with compact support, and therefore this will just give you phi of 0, and you see that this is nothing but delta of phi. So we have th dash equal to delta. Okay, so this is the distribution derivative. So now this raises a certain interesting question. Okay, so you remember that h is a locally integrable function which is differentiable in the classical sense almost everywhere. In fact, you have h dash is equal to 0 almost everywhere. Okay, so th dash, except at the origin, everywhere it is 0, it is a constant function. Okay, so th dash is 0, but th dash equals delta. Okay, so we have this warning, namely if f is in L1 log of omega and is differentiable almost everywhere classical, and f dash is also in L1 log omega, then tf dash is not necessarily equal to t of f dash. So earlier we said that we will not say tf dash etc. We will say f is a distribution. Then when I say f dash, then I have to be careful whether I am talking about the classical derivative or the distribution derivative. Now this is a bit disturbing initially because if these two objects are not the same, so we are wondering what we are getting into. However, for all smooth functions there is no problem, namely because you have the integration by parts formula. You have integral f phi dash is equal to minus integral f dash phi. Okay, so this is always true for all smooth functions, and therefore this will imply, if this is true, so if, so call this star, so if star is true, then of course tf dash will be the same as t of f dash. Okay, so the question is, when is integration by parts formula true? So if integration by parts formula cannot be taken for granted, then of course you have to check. It may still happen that this equation is valid, but you have to be careful, you have to check clearly, check the distribution derivative and see if it comes. So there are many examples where it may happen, but still we have to be not take it for granted. Okay, so example where you do have star. So if f is absolutely continuous, on say an interval a b contained in R, then star is true. Okay, so we in some interval, so let's say this is true. So let us try to prove that this is true. Okay, so let us take f absolutely continuous, say in R for instance. It doesn't matter in any subinterval. Okay, on let's say minus m. Okay, so m is very large. So now let us say phi belongs to d of minus m. That means it's a C-infinity function with compact support. Let us say support of phi is contained in some minus a. So a will be less than m for instance. Okay, so this will be the phi. So now let us look at the set capital A equals set of all xy in R2 such that minus a less than or equal to x less than or equal to y less than or equal to a. So if we have x here and y here, so this is the square minus a by a into minus a by a, and then this is the line x equal to y, and we are having x less than or equal to y is this portion here. So this is the set A. Okay, so on this we are going to evaluate the following integral. I equals the integral over a of phi dash x f dash y dx dy. So I am going to evaluate this integral in two different ways. So on one hand you have I equals integral minus a to a f dash y integral minus a to y. Because x is less than or equal to y, it will go from minus a to y, phi dash x dx, and then you have dy. So the inner integral, if you evaluate, it is phi dash y minus phi of y minus phi of a minus a, but phi is of compact support and therefore phi of minus a is 0, and therefore this will give you integral minus a to a f dash y phi of y dy. On the other hand, this can be also written as integral minus a to a phi dash of x into, now you have to write from x to a. So y will go from x up to a, and x will go from minus a to y. Okay, so this is how they go. X to a, sorry, x to a f dash y dy and dx, and that is equal to integral minus a to a phi dash of x. Okay, being an absolutely continuous function, this is if you recall a definition of what's the definition of an absolutely continuous function. There is a usual epsilon delta definition, but the other definition is that it is the indefinite integral of an integrable function. That is the other definition of an absolutely continuous function, and therefore since it's an indefinite integral of the absolutely continuous function, and you have that the fundamental theorem of calculus is true, so this will give you fa minus fx dx. Okay, so now fa is a constant, will come out. You have integral phi dash from minus a to a, but it vanishes at both end points because phi has compact support. So this integral will just give you minus integral phi dash x f of x dx minus a to a. So you see f dash y phi of y dy is also equal to minus phi dash x fx dx, and therefore the integration by parts formula is true, and consequently you have this formula that the classical derivative, therefore, so this implies f absolutely continuous implies tf dash is equal to t of f dash. So let me recall. So f absolutely continuous on AB implies f of x equals f of a plus integral a to x g of x g of t dt, where g is integrable. And you have so it's that means implies there exists a g integrable such that you have this, and it now every absolute continuity implies bounded variation, implies it's a difference of monotonic functions, which implies that this is differentiable almost everywhere in the classical sense, and you have in fact f dash equal to g almost everywhere. Okay, so you can write f of x equals f of a plus integral a to x f dash t dt. Okay, so this is the revision crash course on absolutely continuous functions. Okay, so we have. So before we proceed to other operations, here's one interesting question. So So if f is a differentiable function and f dash equal to 0, then this implies f equals constant. This much we know. Okay. Now if t is a distribution on R, or on the subinterval of R, on an interval in R, or on an interval what can we say if t dash equal to 0? So what do you mean by saying so t dash equal to 0? Does it mean that t is a constant? But what do you mean by t is a constant? T is a distribution generated by a constant. Is it true that there exists a constant c in R such that t equals tc, that is t of phi equals c times integral phi dx over R? Okay, this is what we mean by the distribution is a constant. So if the derivative is 0, does this happen? Answer is yes. So what do you mean by saying t dash equal to 0? This means for every phi we have t dash phi equal to 0, that is t of phi dash equal to 0 for every phi in d of R. What I am saying for R works for any interval also. Okay, so now we want to know, so question, that phi in d of R, question is, does there exist psi in d of R such that psi dash equal to phi? Answer, yes, if and only if integral phi over R dx equal to 0. So let us prove this. So if phi equal to psi dash, psi in d of R, then integral phi equals integral psi dash over R, and then this is nothing but the difference of psi in the two endpoints, but psi vanishes at infinity and therefore this is equal to 0. So that's one way we have proved. So now let us assume, let integral phi over R dx be equal to 0. So let support of phi be contained in minus a. Okay. Now define psi of x equal to 0 if x is less than or equal to minus a, and is equal to minus a to x if of phi of t dt if x is greater than minus a, greater than equal to. So this is continuous. Now we can check that psi belongs to C infinity, because we have taken the support inside, well inside. Let me say, put it as a open interval here, so that the support will be well inside it, and therefore this will be 0 even after you cross minus a for some time, and therefore this will be patching up nicely, and afterwards its derivative by the fundamental theorem of calculus is nothing but phi, which is a C infinity function, and therefore this function is in fact a C infinity function. Now psi of x is equal to 0 if x is less than or equal to minus a, that we already know. Now if x is greater or equal to a, then psi of x is equal to integral minus a to x phi t dt, okay. But if x is bigger than or equal to a, this is equal to integral minus a to a of phi t dt, because phi is 0 after a, because the support is contained in a, and this is in fact equal to 0 again, because we are given that integral of phi is 0, and consequently therefore you have support of psi is also contained in minus a, and therefore you have this is true. Therefore you have this. So now let t dash be equal to 0, and let us take chi in d of r such that integral chi over r equal to 1. So this you can always find. Take any function whose integral is not 0 and divide it by the integral, then you will have that the integral will be equal to 1. So divide it by a constant, so you will get that the integral equal to 1. So we can in fact have any number of such functions which have this. Now you consider, so given phi in d of r, then you look at phi 1 equals phi minus integral of phi over r times chi. So this belongs to d of r. And what is integral phi 1? Integral phi 1 is nothing but integral phi minus integral phi times integral chi, but this is equal to 1, and therefore this is equal to 0. So implies there exists a psi in d of r by whatever we saw just now, such that psi dash equal to phi 1. Now t dash equal to 0, so t dash of psi equal to 0, that is t of psi dash equal to 0. And what is t of psi dash? T of psi dash is t of phi 1, which is equal to t of phi minus integral phi 1 phi dx over r times t of chi, okay. And therefore t of psi dash has to be 0, so this is equal to 0. So this implies that t of phi equal to a constant times integral over r phi dx, where c equals t of chi, okay. So we have shown that in fact if the distribution derivative is 0, then t has to be generated by a constant function. There is one point which should however worry you, namely we have chosen chi to be any function in C d of r such that its integral is 1. And so if I chose some other function, will I get a different constant? Then there is some trouble in the problem, but you won't, because if chi 1 are such that integral chi equals integral chi 1 equal to 1, then this implies that integral chi minus chi 1 is 0, and this implies that chi minus chi 1 is equal to some psi dash, and therefore t of psi dash will be always 0, and this implies that t of chi minus chi 1, and therefore this implies that t of chi equals t of chi 1. So there is no ambiguity caused by the choice of the chi function chi which you chose. Okay, so this is so much about distribution derivatives for the moment. So our next aim would be to define another operation on distributions, which we will see next.